Can you hear me okay? Do you sound all right? Doing well today? Make sure everything is sounding okay before getting going. Good. Yeah, probably give it a couple minutes, see if anyone rolls in, and then go ahead and get started. Alrighty, I think might as well go ahead and get going. Yeah, so welcome to the stream. I'm actually pretty excited for this one. Should be some interesting stuff, so yeah, let's get into it. As always, of course, feel free to ask any questions might show up. Feel free to drop them in the chat, let me know. I'll try to answer them as I go, or if I get a good stopping point. So what do we want to do today? So we've been doing a whole lot with Hamiltonian mechanics and all this stuff, but we've really kind of tunneled ourselves into only considering a very specific type of transformations to our coordinates, which, has been very helpful, and everything. We've gotten very nice general relations from that, but one of the main ideas of the things I want to talk about today is a more general type of transformation that we can do in phase space, so a more general phase space transformation, known as a canonical transformation. And of course, I'll get into what exactly I mean by that bit. So by looking at these canonical transformations, this will lead us to specifically this idea of generators, generators of transformations, which is actually a very important concept in many branches of physics, but it ends up playing a really big role in, for example, group theory and things like that. And we'll see that in order to express these generators and these transformations, this idea of a Poisson bracket is very, very useful. So then we're going to use this Poisson bracket to get some very fundamental results from Hamiltonian mechanics, but also we're going to see something very interesting happen. We're going to see some sort of familiar relations show up in regards to the Poisson bracket, and using sort of parallels to what we've seen before, we'll be able to do something pretty cool. Okay. So, yeah, let's go ahead and get started. So, up to this point, what have we considered? We've really only restricted ourselves, restricted to transformations where we take our coordinates, we call them Q, some coordinates Q sub L, and we transform them to some different q's, which are all only functions of, I'll use a different index, all of our new q's, so these q primes, are all functions of our old coordinates. So this is what we've restricted ourselves to, and this was really nice because we were able to find a nice, neat form of our Hamiltonian. Just sort of in general, write it down, ij p sub I p sub j plus u sub l. Where in general, I'll actually go ahead and fill these off over here and just explicitly write that this G matrix can be a function of our coordinates. So this is sort of what we've been dealing with up to this point. And of course this led to Hamilton's equations, so the time derivative of the q's is related to the derivatives of our Hamiltonian, and same thing for the time derivatives of the p's, dh, dq sub I. So this has been sort of our structure of Hamiltonian mechanics, provided that this is true, provided that we're always sort of restricting ourselves to these sort of transformations. Yeah, so I do try to read the live chats. I keep my eye on it to hopefully answer any questions that show up. But yeah. Okay, so this is all well and good, but I mean, okay, we might think that there can be some more general transformations that we can do. In particular, last time we talked a whole lot about phase space and how we sort of defined a space made up of both our coordinates and our momenta. So we might think that instead of just transforming to some set of coordinates which are functions of our old coordinates, we might think that we can do a more general phase space transformation. Where our old coordinates, I'll call them q sub I, go to some new set of coordinates, which I'll call capital Q sub I. And these capital Q sub i's are functions of both our old coordinates and our old momenta. And we can do the same thing for our old momenta. I'll say little p goes to big P, which is, again, a function of both our old coordinates and momenta. So you see, this is a much more general set of transformations. So how is this useful? I mean, what can we do with this? Well, first of all, let's not get too carried away with ourselves and consider a bit more simple case where we're just going to look at infinitesimal transformations. Transformations. The reason being is that you can. This is a common thing that we do in physics. We look at very, very small transformations, with the idea being that we can build more general transformations, so something that I'll call a finite transformation. We can build those from infinitesimal transformations. We just do the infinitesimal transformation over and over and over and over and over again. So you can prove a lot of stuff with these infinitesimal transformations with a lot less mathematical heavy lifting. So what we'll consider is some transformation parameter, which I'll call epsilon. And we'll say that epsilon is very, very small. It's a very small number. In which case I can write these transformations, which I'll call Q, again, capital Q for our new coordinates. And these are going to be very, very close to our original coordinates, our little q sub i's. But we're going to transform them by some small amount. Q sub L, E sub L. And this small amount is just going to be determined by this function f, which is, of course, a function of both our old coordinates and momenta. And we can do the same thing with the p's. P sub I plus epsilon, some different function in principle, P sub L. So these guys are our infinitesimal transformations. And these are what we're going to really be looking at going forward. Again, like I said, we can build more general transformations by just doing these infinitesimal transformations over and over and over and over and over again. So basically anything we prove with these infinitesimal transformations carries over to finite transformations as well. So again, let's not get too carried away with ourselves and give us some restrictions. Like what kind of transformations do we actually care about and what don't we care about? Because I mean, in general, we can do basically anything we want. That doesn't necessarily make it useful. In particular, let's not care about what it does to our Hamiltonian. It can change the form of the Hamiltonian all we want. So, I mean, like before, whenever we changed our coordinates q, it already changed our Hamiltonian. So who cares if our Hamiltonian changes? But what never changed was the form of our equations of motion. So we'll restrict ourselves, restrict the transformations which leave the equations of motion, we say form invariant. Just meaning that it's not going to change what the equations look like. I'm just going to be substituting my new coordinates for my old coordinates. So in particular, I care about transformations such that this equation of motion is going to become something basically the same thing in terms of my new coordinates and momenta. Oops. And then same thing here for the momenta. P sub I minus h q sub I. So these are going to be the transformations that we actually care about. These are what we're going to be restricting ourselves to. And these transformations have the special name of canonical transformations. So these are the set of transformations that we can do involving both our coordinates and momenta, which leave our equations of motion form invariant. So it's not going to change the form of Hamilton's equations. Okay. So how do we find these? Is there a more general rule for, can we look at a transformation and say, okay, that one's a canonical transformation, that one's not? It turns out, yes, we can. There's actually a very neat way that we can show that. And it starts by just doing the transformations. So we'll start by looking at the time derivative of u. Remember, this is some function of both our old position and momentum. coordinates. So let's just use the chain rule on this, and we get q sub I dot plus dq dp sub I p sub I dot. And each of these guys, q dot and p dot, we can rewrite using Hamilton's equations. So these just become dq dqi dh dpi minus dq dpi dh dqi. Okay? And we can do a similar thing for the new momenta. Just do the chain rule. I'll make this j here just to not completely screw up all of our indices. J dqi qi dot plus dp sub j dp sub I dot, and again just replace these with Hamilton's equations. Oops, looking at the line above. dh dp sub I minus dp j dq sub I dh d this should be q sub I. This here should be p sub I. Okay, so that's what happens to the left-hand side of this equation here. So that's this part of the equation. So now let's look at the other half. So let's look at the other side of the equation. Now, here I'm going to make a note. We're going to assume that our transformations are invertible. Assume that the transformations are invertible. What does that mean? That just means that I can both write, say, q sub I is a function of little q sub L, little p sub L, but I can invert this so that I can, say, write my old coordinates as a function of my new coordinates. This isn't guaranteed to be the case. There are, actually, we saw in the last stream a case in particular where we restricted ourselves to a subspace. So this isn't guaranteed to be the case, but for a lot of cases, for most intents and purposes, this will be true. So we're gonna assume going forward that our transformations are in fact invertible, which means we can look at this right-hand side, or these right-hand sides of these equations, and again just use the chain rule on them. So we have that dh dp sub I is going to be dh dq sub j dq sub j dp sub I plus dh dp sub j j d sub I. This should be capital. I'll try to distinguish my lowercase and capital P's as much as possible. And then we get a similar thing for dhdq. J, q sub j, big Q sub I, plus dh dp sub j, dq sub I. So now all we have to do is equate I'll do this one in red. So equate this equation with this equation. And then equate this equation. I'll do this in a different color. How about purple? This guy with the minus of this guy. Right, because that's just Hamilton's equations. That's just up here, right? Q dot is equal to dH dP. So that's this guy. And then similar for P dot. So you can see that similar terms are showing up in both, right? So we have, in particular, I'm running out of colors to use. I'll use this. I'll increase the size of it a bit. So here I have a dH dQ sub I. And over here, I have a dH q as well. Similar here and here. And similar for the P dot equation, right? So I have the dH dPi, dH pj, and same thing here. So for these things to be equal, one way of doing that is just essentially everything, wherever I match these cyan boxes up, I just equate their coefficients in the correct way, keeping in mind the correct signs and all of that. Right, so I would equate this term with this term, and I'd equate this term with this term, and so on, because the factors of dH dQ or dH dP match up. So when I do that, I get 4 different equations. I get dq sub I, dq sub j is equal to dp sub j, dpi. I get dq sub I, p sub j is equal to dq p sub I. So this comes from q dot I equals dH dP sub I. So these two equations come from that. And then I get 2 more equations, dP I, this should have a minus sign, sorry. Qj is equal to minus dpj dqi, and then dpi dpj equal to dqj qi. And these come from p dot I minus dH dqi. Okay. So these are our requirements for canonical transformations. But we can do better. We can do better than this. This is good, but it's still not quite great. So now remember, we're dealing with infinitesimal transformations. That's what we care about. Want infinitesimal transformations. Which means that anything, we don't care about anything which is going to be epsilon squared or greater. We don't care about any terms that are higher order than epsilon to the first. We can essentially just throw all those terms out. Which means that, so when I have my transformations, qi, ql, pl equals qi plus epsilon fi, ql, pl, and same thing for p, pl, pi plus epsilon gi, l. When I have these, I can find the inverse of them by essentially just subtracting these functions from both sides. So, I mean, I can just do that. And I find that q sub I is equal to big Q sub I minus epsilon f sub I little ql, p sub l. And then p sub I is equal to big P sub I, Q sub L, P sub L. Won't even write that. Minus epsilon P sub I, Q sub L, P sub L. So you can see that now I've almost written my Q's and my P's in terms of my little q's and p's in terms of big Q's and P's, except for whatever lives in these f and g functions. But I can replace whatever lives in these f and g functions by just applying these rules. So, for example, f is going to be big Q sub I minus epsilon f sub I, and then p is going to be big P sub I minus epsilon g sub I. Now, epsilon is very small, so I can expand this function, and I'll get something which looks like Q sub I, P sub I, plus order epsilon terms. I'm not going to care about the order epsilon terms, though, because this f is already multiplied by epsilon. So if I have a term which looks like, I don't know, epsilon times some, I'll call it other function little f, then when I plug this back in here, this term will end up being epsilon squared, which I just said we don't care about. We don't care about anything higher than epsilon to the first. We only care about epsilon to the first because these are infinitesimal. So, keeping all that in mind, just to my desired order in epsilon, I can actually just erase this stuff real quick. I can just replace everything in here with the big P's and Q's. Q sub L, P sub L, Q sub L, P sub L. And this is my inverse transformation. So this is the inverse. So these guys are my canonical transformations. This is the inverse of it. Which means we can now take all of these derivatives that we have up here. So we have to take 8 derivatives total. And then we can just do those and then set them equal to each other. There is one final note, and it's along these lines. In particular, if I have something like df dq sub I, dfj, this is going to be equal to, df. So this is going to be equal to df d little q plus, again, order epsilon terms. So keeping this in mind, you can see that whenever I take a derivative of, say, d little q with respect to big Q, I can always rewrite that back in terms of little q, since those derivatives will show up with an epsilon in front. And so really this will end up showing up something like this, and this will be epsilon squared. Hopefully that makes sense. I'll write it out a bit more explicitly here. So, for example, again, let me just get this out of the way. I can start by taking the q sub I, the little q sub j. And this gives me a Kronecker delta, delta ij, when I try to take the derivative of q sub I with respect to q sub j. Plus epsilon df sub I dq sub j. That one's pretty straightforward to do. I have dp sub I dq sub j. Well, this term here, when I take the derivative with respect to a coordinate, just drops out. That one just goes to 0. So I'm only left with the derivative of this second term. This is epsilon dg sub I dq sub j. And keep going. You see a similar thing happening with the derivative of q with respect to p. The q term drops out, and I'm left with epsilon dfi dpj, and then pi ej. Again, I get a delta ij term plus epsilon dg e. Now I have to take the derivatives of these guys with respect to my new coordinates. So I take the derivatives of my old coordinates with respect to the new coordinate, right? Because that's what was showing up on the right-hand side of these equations. So I can do that. Just start simple, this guy. Again, I get a Kronecker delta term when I just try to take derivative of big Q with respect to big Q. And now I get minus epsilon df sub I d big Q sub j. Like I said, this is already order epsilon, and any difference between the derivative with respect to big Q and the derivative with respect to little q is going to be order epsilon. So since this is already multiplied by an epsilon, those differences are going to be higher order. So I don't actually care about them, and I can just replace this big Q, little q. Okay. And then I can keep going with this. I can look at d little p sub I, d big Q sub j, and I get minus epsilon d g sub I, d little q sub j, and then q sub I, p sub j is equal to minus epsilon df sub I, d little p sub j, and then dp by big P sub j, delta ij minus epsilon dgi d little p sub j. So now I have explicit forms of all of these derivatives in terms of these transformation functions, right? These transformations that I'm doing are defined in terms of these f and g functions. And so now I can use these equations up here that we found, so these guys, plug these, all 8 of these derivatives into those equations, set everything equal, and move on with my life. So when we do that, we can sort of crank through the algebra, whatever. We get 3 independent equations. Well, 3n squared because of the indices, but really 3n that we care about. Fi dq sub j is equal to minus dg sub j dp sub I. So that's our first equation. Our second equation is, I'm going to space these out a little bit more. You can still see that. df sub I dp sub j is equal to df sub j dp sub I. And then our last one is dg sub I dq sub j dg sub j dq sub I. Okay, so now all of this complicated stuff, and now we have relations between our transformation functions, our f's and our g's. In particular, these two last ones are very interesting because you can see that they're almost trivial. It's almost essentially a is equal to a, except for the fact that going from the left-hand side to the right-hand side, I'm flipping the indices. So this essentially tells me that these derivatives are symmetric in their indices. That's how we say it. Yeah. So I can replace the index of this function, this vector function, and I can take that index and flip it with the index on the derivative. And I get this exact same thing. So now I'm going to use a very hand-wavy argument, which can be proven in much more formal, in a much more formal way. But so we already sort of know of a function that does this, that involves derivatives. And that's just, if I had a second derivative of some function, we'll say dqi dqj, this is equal to d2f dqj dqi. Right, because I can commute derivatives. I can move them past each other as long as they're independent derivatives. So this very simple relationship, I'm going to say, is it going to inspire us to rewrite f sub I is equal to df dp sub I, right? Because this one involves a p derivative, this one involves a q derivative, and so I'll write g as dg dq sub I, little g and little f. Where now little f and little g are scalar functions. They're no longer these vector functions. And f is equal to f of q and p, of course. Same way as before. Now, I will note this, yes, I admit that this is incredibly flimsy, a very flimsy argument to say that, okay, these are taking this form because of this slight comparison to derivatives. But this is actually true. This is true in general. This is actually the only form you can have for these functions. And the proof comes, you can prove it from the n-dimensional Stokes theorem. We could get into this, but I don't really see it super relevant for this discussion. So, something to look into if you want to see that this is indeed true in general. But it is. And we can write our functions in this form, our transformation functions in this form. So now let's take a look at our third equation here. Well, we can use what's in the red box and just plug it in to this third equation. And we get that d2 f dq sub I dp sub j is equal to d2 g, or minus d2g, dp sub I dq sub j. And this is actually something that we can solve. We can just go ahead and solve this equation, and hopefully it's somewhat straightforward to see that g of q sub L e sub L is equal to minus f q sub L e sub L plus a constant. This is sort of the general solution to this sort of equation. So now we have our general relation between our transformation functions, and we can go ahead and just plug this in to get our most general form of a canonical transformation. Transformation. And this looks like I take my q's and I replace them with my big Q's, and this gives me q sub I plus epsilon df dp sub I. And then I take my p's, that looks, try to emphasize that that's a small p, big P, which is p sub I minus epsilon df q sub I. So you see that the same function, I choose a function f, and the same function gives me the transformation in both p and q. It just comes with a separate sign. So this is what we'll define as our canonical transformation. Well, it has to be this in order to keep our Hamiltonian form invariant. So I know I just threw a whole lot of math at you, so I'm going to take a quick second to pause, drink some water, see if anybody has any questions. Feel free to drop them in the chat. Yeah, so hopefully we can sort of appreciate how powerful this is, that, you know, we've been able to find a complete general class of transformations, which allows us to keep our Hamiltonian equations in the same form. So essentially, no matter how we transform, as long as it looks like this, our equations of motion will always have this same form. Q dot equals derivative of h with respect to p, and p dot is minus derivative of h with respect to q. Okay, so I'm not seeing any burning questions showing up in the chat. So here's what I'm going to do. We're going to look at what happens now when I do one of these canonical transformations for a general function. So I'm going to take a general function, and I'll call it psi, q sub L, p sub L, just because I'm running out of names of functions, so might as well go to Greek letters. So now we want to do a canonical transformation, we do a canonical transformation. Using the rules that we just found. And in particular, we can use the rule for just expanding a function to some set order, well, to first order in epsilon. Namely that if I have some function phi, and it's phi of x plus epsilon, this is going to be equal to this 5x plus epsilon d phi dx with epsilon equals 0 plus higher orders. This is just a Taylor expansion in a small parameter. That's all I've done here. So when I do this, I have psi of q sub l p sub l goes to psi, call it psi prime, of big Q big P, which we know is equal to psi prime of our canonical transform coordinates. So this is df dp, and then p minus epsilon df q. Now I just do this expansion to first order in epsilon, and I get that this is equal to our original function, psi ql p sub l, plus my first order in epsilon term. So this is d psi dq, because I'm taking the derivative of this part first. And then I get the piece which is proportional to epsilon, which is df q, and I should be summing over my indices. Sum over indices, plus, actually minus, the part where I'm expanding in p. So this is d psi dp sub I, df dq sub I. And this is, of course, plus order epsilon terms. So now I'm going to make a definition, and I'm going to say that this is equal to this, my old function, plus epsilon times this wacky thing, plus order epsilon, where I've defined psi f, that looks like a 4, psi f is equal to d psi d q sub I df d sub I minus d psi dp sub I df dq sub I. And this is known as the Poisson bracket. It's just a definition, that we make. So you can see that here I've, of course, used the summation convention, where if the indices are repeated in a term, then I'm assuming that they're summed over, unless I say otherwise. So I sum over all of the derivatives of the first function with respect to all of my q's, and the second function with respect to all of my p's. And then the next term, I essentially subtract from that all of the flipped derivatives. So derivatives of the first function with respect to p's and the second function with respect to q. So this is my Poisson bracket. And this is actually pretty cool, because let me just write this down again, that the effect of any canonical transformation on any function is given in terms, I'll say generated by the Poisson bracket. So psi of q sub l p sub l, it transforms by the rule s plus epsilon psi f. So this Poisson bracket, plus order epsilon squared term. This Poisson bracket is what is determining how this function transforms. And so that's why we say that this Poisson bracket, and particularly this function here, generates the transformation. So this f function we call the generator of the transformation. So whenever I say generator, all this means is that this is the function which determines my canonical transformation, right? My canonical transformation is determined in terms of a single function f, and that's what I'm going to call the generator. So this is all well and good. This is great, but we've neglected a very important piece of the story, and that's, of course, time. So, in even more general, I can consider a psi where, of course, all my coordinates are functions of time, all of my momenta are functions of time, and psi can be an explicit function of time itself. So now what I want to do is I want to consider the case where I do some shift in time, right? So I want to essentially look at how this function is going to evolve with time. So I'm going to do a very similar thing, and I'm just going to take time, and I'm going to shift it to t plus dt. So some infinitesimal shift in time, just to see how this function is changing. And of course, I can write that sub l t plus dt e sub l psi prime t plus dt, and then t plus dt explicitly. Now, like I said, this dt is infinitesimal. So I can do this exact same expansion that I found before. And what I find is that this is equal to, I'll write psi of q e t, so our original function, plus dt times, I'll write the psi dt as a hard derivative. So this is my total derivative with respect to time, not just a partial derivative, which means I have to pick out the time dependences in each one of my terms. So I can write that a bit more explicitly, dt, and now I can just use my chain rule like normal. D psi dq I qi dot plus d psi ei ei dot plus d psi dt. But now I can rewrite both of these guys using Hamilton's equations. And I get qpt plus, and of course this is plus order dt squared terms. Always make sure to write those in. Plus dt times d psi dqi dh dpi minus d psi dpi dh qi plus d psi t. So what do we notice? We notice this term here looks a little bit familiar. And in particular, that's just our Poisson bracket showing up again. And more exactly, it's our Poisson bracket between our function and the Hamiltonian, psi comma h, psi t. So going back to this equation here, I'm going to just pick out the time derivative term, the total time derivative term. And I can see that my total time derivative, so my evolution through time, is given in terms of my Hamiltonian, the Poisson bracket with the Hamiltonian, plus whatever explicit time dependence psi has. So again, this here, right, h, as long as we have a conservative system, h is a function of q and p only. Which means that this Poisson bracket, which is essentially giving us how our system evolves through time, this is just a canonical transformation. But we see that the generator in this case is the Hamiltonian. And so what we typically say is that the Hamiltonian generates time evolution or time translation. Because however much I move in time is governed, say psi doesn't have an explicit dependence on t, so I can sort of ignore this term. That's not true in general, but say for argument's case, in this particular circumstance it is, then the entire evolution of the function is completely determined by our Hamiltonian. So this is actually a very important statement that we will get back to. Well, actually, we'll look at a consequence of it now. But maybe I'll take another pause here. A quick pause, drink some water, see if anybody has any questions. Feel free to say them. Should we be entirely surprised that the Hamiltonian is what generates our time translations? Maybe, maybe not. I mean, we already saw that, our equations of motion are already entirely governed by our Hamiltonian, so it's not super surprising necessarily that the Hamiltonian is what is the generator for time translations, but it's still nice to sort of see it explicitly. Okay. Okay, so now let's go ahead and let's go ahead and look at something, an interesting case. So what we're going to do is we are going to take, so before I had this function psi, q, p, and I'm going to replace it with my Hamiltonian. Right, Hamiltonian is just some function of q's and p's, just like the psi was as well. And now I'm going to make a canonical transformation. Make canonical transformation generated by some function f, little f. So we already saw that when I make a canonical transformation, I can write it as, so my Hamiltonian in terms of my new coordinates is written as my Hamiltonian in terms of my old coordinates plus epsilon times h comma f plus order epsilon squared terms, higher order epsilon terms. I don't really care about. Okay, so now here's a interesting point. If the transformation is a symmetry of the Hamiltonian, then that means that my transformed Hamiltonian cells, I'll make cells as well just to sort of stay consistent. Our transformed Hamiltonian should be exactly equal to our old Hamiltonian. Q, E. So that's the case that this transformation is a symmetry. But of course, the only way for that to happen is if this Poisson bracket vanishes. But now remember, our f, our canonical transformation generator, is given just in terms of q's and p's. It's not given in terms of time. So it's not an explicit function of time. Which means that when I have this Poisson bracket here between f and h, this term here is going to drop out, and so it's just going to be exactly equal to the time derivative. Really the minus, because as I'll get to in a second, the Poisson bracket is anti-symmetric in its arguments. So h comma f is equal to really minus df dt. That's equal to 0. So this means that my total change in f with respect to time is guaranteed to vanish when I have a symmetry of the Hamiltonian under a canonical transformation. This is just another way of saying that f is conserved. Right? It doesn't change with time, it's just a number with respect to time. Total time translations, keep in mind, because each of these q's and p's are functions of time themselves. So here, yet again, we're seeing, sort of step by step, deeper and deeper, how symmetries are very deeply connected with conservation laws, right? So now we're saying that I'll actually write this down because this is very important. Any canonical transformation, any canonical transformation which is a symmetry is a symmetry of the Hamiltonian directly corresponds to a conserved quantity. In particular, it's the generator of the transformation. So whenever I make a canonical transformation, and that canonical transformation ends up being a symmetry of the Hamiltonian, the generator of that transformation is guaranteed to be conserved. Very, very cool stuff. Again, sort of this connection between math and physics, right? The math side is a symmetry, which is a very, which a lot of times, is somewhat abstract, what the symmetry is and everything. And it's corresponding to, in a lot of cases, a physical conservation law. So something like conservation of momentum. I'll show in a second what all that means. But so again, we see this super deep connection between the two. And it even is slightly deeper than this. But that comes from, the proof of that typically comes from Lagrangian mechanics. So this is very cool in and of itself. So now I want to just go over some very, very quickly some properties of the Poisson bracket. Properties of the Poisson bracket. And I'm not going to prove these. They're easy enough to just prove by the definition. And in particular, a lot of them just come from the linearity of derivatives. So the first is that it's antisymmetric, as I said, minus g comma f. That's the first one. It's antisymmetric. Antisymmetric. Just meaning that if I exchange the functions, I get a minus sign. The second one, well, really the second and third one together sort of come from linearity arguments. And this is just that if I have three functions now living in my Poisson bracket, this is given by just that relation. And again, this is fairly straightforward to prove just using rules of derivatives. So I'm not going to go super in depth about with these proofs. The last one is sort of very clearly, well, this isn't the last one, but very clearly comes from linearity. And that's just that f plus h comma g is just the sum of Poisson brackets. Yeah, and so both of these just come from derivative rules. And then finally, we have the Jacobi identity, which is, it's fairly easy to prove, but it's very tedious to go about showing it, because you have to expand all these things out in terms of derivatives, and so you end up with just tons and tons of terms, but of course they all end up canceling, and Jacobi identity works out very nicely. And this, yeah, as I said, Jacobi identity. So whenever you have a Poisson bracket that is structured, or a sum of three Poisson brackets, which is structured like this, it vanishes. So yeah, like I said, all of these are, they're fairly straightforward to prove. The Jacobi identity, like I said, it's simple to prove, but it's very, very tedious. So these are just some sort of important properties. But now I want to move on to a very interesting example, which may not seem that interesting at first. But let me assure you that it will be very interesting. And that's If our generators, first we'll consider the case where the generator is given by the momentum. Just one of our canonical momenta. Well, in that case, we can write out our Poisson bracket from a p. And this is, of course, d psi, dq sub j, dp sub I, dp sub j, minus d psi, dp sub j, p sub I, dq sub j. This term here is going to give me a Kronecker delta. This term is going to go to 0. That's going to vanish because my momenta and coordinates are independent. So this just is d psi dq sub j. Okay. So what action does this actually have? So if I have a function, and so function psi of q and p, what does this canonical transformation actually do, generated by the momentum? Well, we already know that the transformation is given by, it just is our old function, plus epsilon times the Poisson bracket. So in this case, I have to slap an index on epsilon because really I have to sum over all of the momentum generators I may have. If I only have one, then that epsilon will be the only non-zero one, but in general, I'll sum over all of my epsilon, or sum over all of my possible momentum directions. And this is just d psi dq sub j. Oh, not j, sorry. This should be I, because I'm summing over all of the, basically all of these different Poisson brackets corresponding to the different momenta I may have. But as we already saw, this is, okay, I'll plus order epsilon squared. This is just an infinitesimal shift in my coordinate, right? Q sub L plus epsilon E sub L. So the momentum, we say, generates spatial translations. So if I make a canonical transformation where it's generated by a momentum, then I know that that is just going to end up giving me a shift. It's just going to translate me in the corresponding coordinates. Okay. So now we can do a similar thing, where now we'll consider what happens if, consider the generator is a coordinate, q sub I. Well, now we just, we do the same thing. We find the Poisson bracket first, q sub I. And by similar means, we find that this is just minus the derivative with respect to p. And so then psi is going to transform to psi, now minus, because of this minus sign here, epsilon I psi dp sub I plus order epsilon squared terms. Which again, is, of course, is just this guy. Now minus epsilon. So here we see that our coordinates generate momentum shifts. Okay. So, okay, so I'm gonna write down these relations here. Psi e psi d psi q sub I of psi q sub I equals minus psi e sub I. Okay, so now with this in mind, so these are essentially the ways that I generate respective shifts in either position or momentum. So now I'm going to pause here and I'm going to pose a question. Feel free to answer in the chat if you like. Does this look familiar? Do these relations look familiar at all to you? I mean, have we seen other relations which give something similar to this structure? I'm going to take a pause here, drink some water. Feel free to leave it in the chat if you like. I guess specifically, the structure where, I mean, sort of this combined stuff. Does this ring any alarm bells or give you any, not red flags, but does it remind you of anything? This is where things start to get very cool, I will say, in my opinion. Okay. So let's say that I'm going to give you a reminder of what happens when I have a Fourier transform pair. So in this case, I'm going to have a Fourier transform pair, which I'm going to call, so Fourier transform pair, x and k. So these are just going to be Fourier conjugate variables. So I'll just write out the relations. So I have my Fourier transformed function to the ikx. F tilde k is equal to 1 over 2 pi integral minus infinity to infinity dx f of x e to the minus ikx. Okay, so these are Fourier transform relations. And now what I'm going to do, so here I have some operator, right? It's my Poisson bracket's essentially an operator. It's got derivatives living in it, so on and so forth. With the function that I care about, as well as one of my coordinates, and that spits out a derivative. And same thing over here. I have my function, I have a coordinate, and it gives me a derivative. Notice that in each of these, the derivatives that I get are opposites, and it comes with a relative minus sign. So this is almost exactly the same as what we find from a Fourier transform pair. Just to remind you that I can write I minus I times df dx is equal to the Fourier transform of k, f tilde of k, e to the ikx, and similar here. This is equal to 1 over 2 pi, so the inverse Fourier transform, dx, f of x, e to the minus I kx. So we see an almost identical structure forming, right? I have some operator where inside I have my function times one of my variables, I have my function and one of my variables, and then it spits out a derivative of the opposite variable with a negative sign between them. So I'm seeing a completely analogous structure. Now, I can't necessarily say that these are equal to each other by any means. That I can't do. But let's ask a question. Let's see what happens. Now, again, this doesn't follow directly from Poisson brackets, right? These are just statements, some operators. But the comparison, the fact that there's so many similarities between these two things, might lead me to ask the question of, hey, what if my Q's and P's are Fourier transform pairs? Right? Just because, I mean, again, there's so many similarities between these two structures that it might seem to lead us to, draw a much more direct comparison and see what happens if we go ahead and try to essentially try to force our P's and Q's to be Fourier transform pairs. So, and write it out, keeping in mind that in general I'll have n P's and n Q's. So in general, we have n P's and n Q's. In this case, I can write some function of Q, which again I'll keep calling psi, as my integral over all of my P's. I'll just represent my integral over all P's as dnp of the Fourier transformed function psi tilde, which is going to be a function of the momenta, and e to the I, p sub I, q sub I, right? I'm summing over all of these. Essentially, I'm just doing n Fourier transforms and combining the exponents into a single sum. But here we have to be a little careful because the term in an exponent has to be dimensionless. It can't have units to it. Where momentum and the product of a momentum and a position will not give me something dimensionless. It will not give me something unitless. So I'm just going to divide this by some constant, some number. I'm going to invent a number, throw it in there, so that the exponent has the correct dimensions. And in fact, the dimensions of A are just the dimensions of momentum times the dimensions of coordinate of distance, which just coincidentally is the dimensions of angular momentum. Okay. Now I can invert everything. I can do the inverse Fourier transform. And this is going to look a little bit weird, but just bear with me. I have to have the 1 over 2 pi, but I have to have n of them because, I mean, I'm doing n Fourier transforms or n inverse Fourier transforms. But also, this weird factor of a here messes this up as well. And it turns out that that shows up in this sort of overall normalization. Q psi q e to the minus I p sub I q sub I over a. So this is my Fourier transform relation. And again, this is completely no longer Hamiltonian mechanics. This is no longer even classical mechanics, right? Because we know from looking at wave mechanics and all of this that when I do a Fourier transform, I can't have something be a function of both coordinate and its Fourier conjugate. I can't do that. It doesn't make sense because I'm integrating over all of one of them. So it doesn't make sense to talk about a function of both simultaneously, which of course we know can happen in classical mechanics. We write those down all the time, which are both functions of all of our p's and all of our q's. But so anyway, we're asking what if? What happens here? So let's just keep going with this, right? So okay, so in the space of q's, so from this point forward, I'll refer to coordinate space. Coordinate space, which is whenever our functions are functions of our q's, and a momentum space when all of our functions are functions of p's. Okay? So in coordinate space, I can write down just some whatever q sub I times psi q sub I, right? It's just some product. But now if I want to write this same product in momentum space, I have to Fourier transform this, right? Actually draw a double arrow here. I'll just write the Fourier transform as this fancy thing, just meaning that I'm taking the Fourier transform of this thing. And this is going to be equal to I times A times d psi dp sub I. Psi tilde, sorry. Remembering that now over here is coordinates, over here is momentum. Now notice that this is just I, A times the Poisson bracket between these guys. So just sort of really reiterating this fact that we're making essentially an identification between a Fourier transform and a Poisson bracket. We're just identifying these two things, essentially. We can do a similar thing for momenta. And so over here in momentum space, I can just write a product. Isabel. And over here, I want the inverse Fourier transform, e sub I, psi tilde. And this is minus I, A, psi tilde, dqi, which is I, A, times the Poisson bracket of p sub I, q, or psi, q, l. split this up a little bit more. So again, just sort of reiterating this identification between Poisson brackets and Fourier transforms that we're making. Okay, now all of this is, I mean, it's a little bit clunky. It's a little bit clunky. We always have to specify what space, I mean, we should always specify what space we're working in anyway, but we'd like to do things in a bit more general form. In which case, we're just going to define it. Define position and momentum operators. And these operators are going to be linear. Just by nature of either just a product or the fact that they're written as a derivative. And we're going to represent them by Q hats and P hats. Where, again, I'll draw this sort of table in position, so coordinate space. And momentum space. So over here, I'll have that Q hat I acting on psi of Q is just Qi psi of Q. And then in momentum space, I have Q hat I psi tilde of P is equal to IA P psi tilde dq, or sorry, dpi. And I can do the same thing with the p's. Minus ia psi qi, and then p hat I psi tilde p is equal to just p psi. Yep. So I've just defined these things to act in this way. This is just how they behave. I'm just saying that's what they are. Condenses notation. Okay, so now we might have some very interesting realization. You know, we can look at this long enough, whatever, but if I have, say, let's work in coordinate space. Work in coordinate space, which means I'll define psi q. Let's look at what happens if we first act. So we'll say we're going to look at this, acting on psi ql. So I first act with a moment or a position operator, or coordinate operator, whatever you want to call it, and then I act with a momentum operator. And then I'll flip the story. I'll do the opposite. P hat I psi q sub l. And I'm going to do everything in coordinate space because, I mean, it's straightforward to do. I could do it in momentum space as well, but it doesn't really matter. So this is minus IA times d by d q sub I, q sub j, psi q sub l. So that's this first term, minus q sub j, d psi d q sub I. And I'm doing the minus sign just to see if these are different, right? If these are exactly the same thing, right? If the ordering of these operations matters, or if it doesn't matter, then this should give 0. If it does matter, then this should give something non-zero. Well, I can, of course, expand this first term out to give me IA I'll just get a dqj, dqi, psi ql, plus q sub j, d psi dqi, minus q sub j, psi qi. These terms drop out. This guy gives me a Kronecker delta. And I see that this is just equal to minus IA times psi q sub L delta ij. And so we see that if I is equal to j, the ordering of p hat and q hat matters. So it actually matters if I act first with the momentum operator and then I act with the position operator, or vice versa. Okay. So we're going to give this relation a name, and in particular, we'll define this guy as q hat I p j minus p hat j q I, which is minus I a delta ij in our case. Or I guess, sorry, other way around. It's positive IA delta ij, because I've flipped the order of these guys. So I called this term positive above and this term negative above. So I just flipped a total sign, and that's why this sign is different here. So this sort of thing is known as a commutation relation. And in particular, this is known as the canonical commutation relation. Where this thing here, this thing in brackets, is what we call a commutator. It just tells us whether it matters the order of these operators that we act with. Now, something interesting to note is that this commutator, q hat I, p hat j, and actually the reason it's called the canonical commutator is I a delta ij. This is exactly the same, actually, as I a times this Poisson bracket between our classical position and momenta. And actually, the reason why this is called the canonical commutation relation is because this this Poisson bracket is unchanged for canonical transformation. So whenever I make a canonical transformation, this Poisson bracket doesn't change. And so that's how this gets its name of the canonical commutation relation. And this is straightforward enough to prove. I mean, it's about a line, but I won't get into it here because I want to move on. Keep going. Okay. So I guess this is a pretty okay pausing point. Should stay hydrated. Drink some water. Open it up for questions. So I'm sure by now many people see where this whole story is going, what we're actually doing, what this whole what if question actually. But I've always thought this is kind of cool to sort of see unfold, see these connections being made. Okay. So let's keep moving on, keep chugging along. So, let's go ahead and go back to this idea that we were talking about before in terms of generators and transformations and all of this stuff. We'll start by looking at just go back to this idea of a coordinate transformation, or a translation, sorry. And we'll do an infinitesimal translation again. So, translation by some, I'll call it alpha I. So that my q's go to qi plus alpha I. So then I can look at what happens to this, just a random function psi, which is a function of coordinates, not momenta, because remember I can't, since they're Fourier transform pairs, I can't have a simultaneous function of both. So this, we already saw, is equal to q sub l plus alpha I deep psi dqi plus order alpha squared terms. But now I can rewrite this in terms of operators, right? We're trying to get everything in terms of operator notation. So let's go ahead and rewrite this in this fancy way. Alpha I e hat I acting on psi ul plus order alpha squared terms. So you see again this idea of a generator showing up, where now the generator is the momentum operator. Momentum operator is what generates translations. And so actually, let's take this one step further and find a finite transformation. So keep doing this keep doing these transformations over and over again. So all we really have to do is assume that alpha is finite, and then just keep expanding. We keep expanding to higher and higher orders in alpha. And what we get is just it's a Taylor series. N equals 0 to infinity of 1 over n factorial I over a to the n, right? Because each time we expand, we're going to get another factor of, we're going to get another derivative here, which means we need another factor of p, which means we need to kill off this factor of minus ia, which means, that's where this I over a to the n term is going to be coming from. And then just staying consistent with indices is sort of the, I1, alpha I2, ... however high, or however many terms I'm going to. And then p hat I1, p hat I2, p hat IN, acting on psi of q. So this is, I mean, this looks awful, but we can kind of collapse it down into a much more compact notation, into an exponential. And this notation might look a little strange, but it's much more, like I said, much more compact than really anything else. So, you know, what does it mean when I have an exponentiated operator like this? Well, that just means I can rewrite it as exactly this sum, right? Where I got this because, in general, I can write something like this as x to the n over n factorial. So that's just where this sort of notation comes from. So remember, whenever you see an exponentiated operator, it's really shorthand for this sum here. But we use that notation a lot, so it's definitely something to get comfortable with. Okay, so we can do a similar thing for momentum. So say I have E sub L plus beta sub L. In which case I can do the exact same steps, and I find minus I over A, beta sub I, hat sub I, where the relative minus sign between the two essentially just comes from you can see it as the relative minus between the Fourier transform relations, you can see it as the relative minus between the derivatives in the conjugate spaces, etc., etc. So in general, we see that a finite transformation is represented by an exponential of the generating operator. So for example, I might write, if I have some translation operator, I might write this as t. And this is going to be some function of alpha. So this is going to have some transformation parameter associated with it, telling me how much I'm translating by. And this is going to be defined as this exponentiated operator. So this is alpha I, p hat I. For now, I can simply write t hat alpha acting on psi of ql is equal to psi of ql plus alpha l. Okay, so this is sort of this sort of introduction to this operator notation, but this sort of thing is very common where we see some exponentiated operator defining another operator. And that operator is going to do some transformation function. Okay, so this is great, but yet again, we are neglecting time, right? We did it before and we're doing it again. We have a tendency to ignore what's happening with time, even though it's quite arguably the most important element to all of this. So, with all of this said, we can ask the question of how do we evolve in time? Well, we know that in classical mechanics, so Hamiltonian mechanics, we just saw that the Hamiltonian generates time translations. Right, so our Hamiltonian is what actually determined our time evolution in just classical mechanics. But we also know that the Hamiltonian also gives the total energy of a system. Again, classically. So what I'm going to propose is that we introduce a Hamiltonian operator, right? So we're going to take our classical Hamiltonian, and we're going to upgrade that bad boy. And we're going to upgrade it to a Hamiltonian operator, slap a hat on it, which is the same Hamiltonian, just with all of the p's and the q's replaced by their operator counterparts. And we're also going to suppose that there's some space, which I'll call energy space. Such that if I have a psi in energy space, it's going to be a function of the energy and whatever other stuff I may have. So this could be q's, this could be p's, this could be whatever. Not simultaneously, of course, but it could be whatever. I'm going to ignore what else is going on in this argument right now, because it's somewhat irrelevant. Now I'm going to define my Hamiltonian operator so that when it acts on something in energy space, it gives the energy. And this is just inspired by the fact that classically the Hamiltonian just gives the energy of the system. So whenever I'm working in the space where functions are defined in terms of energy, I act on it with my Hamiltonian, and I get the energy. But again, we already saw that the Hamiltonian is what generates time translations, right? In particular, say that we have some phi, which is not a function of t, then we saw that d phi dt is given in terms of this Poisson bracket. Now, this is very reminiscent of what we just did with position and momentum, where we had a derivative equal to a Poisson bracket, and what lived in this derivative was the Fourier conjugate to what lived in the Poisson bracket. So, again, sort of by analogy, we will suppose that t and so time and energy are Fourier conjugates. So now I'm just, again, inspired by what's happening in classical mechanics. I'm imposing this. Time and energy are Fourier conjugates of each other. So that now in time space, so in time space, or the time domain, I might say, I have some functions, I'll call it capital psi to sort of keep it differentiated, and this will be a function of time, etc. And I can relate the two through just Fourier transforms, of course. So psi, big psi of t, is equal to integral from minus infinity to infinity e psi e to the minus I e t over a. Again, notice this factor of a. It's the same a that I was using before because of the fact that the units of e times t are also the units of e times q. So actually energy times time also has the same units of angular momentum, so I can ensure that this exponential is dimensionless if I use the exact same constant, which is very convenient, and actually probably an indication that this is not the most unfounded thing, that we're just sort of introducing a single new constant and everything is sort of consistent. So now I can look at energy space, and again I get this 1 over 2 pi a integral from minus infinity to infinity dt, capital psi of t, whatever else I don't really care about, e to the I e t over a. So now, when I take my Hamiltonian operator and I act on psi, which is a function of t, well, we already saw what happens. I get I a times the derivative with respect to t. Now this might be a very familiar equation to you. In particular, if I replace this constant, which I've called a, I'll give it a new name. That new name will be h bar, Planck's constant. Then this equation here just becomes I h bar d psi dt equal to h hat psi. And this, of course, is the Schrodinger equation. And we have now arrived at quantum mechanics. So this is, I think, very, very cool. All we've done is we've supposed that these Poisson bracket relations, we've essentially replaced the Poisson brackets with Fourier transforms. That's kind of all we've done. And out fell quantum mechanics. So really, we can see that quantum mechanics is really just a statement about Fourier transforms, and the Schrodinger equation in particular. And we can see this a little bit more explicitly by just solving Schrodinger's equation. So for a conservative system, we know that h is not an explicit function of time, which means that we can just, again, solve this equation. And we find that psi of, I'll write it as t plus tau, plus, again, whatever other stuff I don't really care about. I'll write in terms of a time evolution operator times psi of t. Less of this, where this is just going to be e to the minus I over h bar h hat tau times psi of t, etc. But this shouldn't surprise us, really, because, well, we can write this as a Fourier transform relation instead. And in fact, I'm actually just going to transform this guy here. So this is x minus I over h bar h hat t integral minus infinity to e psi of e. So my energy functions, e to the minus I et over h bar. Well, I know that h hat times psi of e is going to give me just the energy times psi of e. And so when I take this exponential minus I over h bar, h hat tau, times psi of e, you can see that this is just going to be a product of a whole bunch of h's, right? So this is a sum n equals 0 to infinity of minus I over h bar to the n, 1 over n factorial, h hat times tau the n acting on psi e. And now I just act with all of my h bars, or h hats. I just keep acting and acting and acting. And this is going to give me n equals 0 to infinity minus I over h bar to the n, 1 over n factorial. Because every time I act with an h hat, I get a e. It's tau to the n, psi of e, which of course I can rewrite in terms of an exponential. Minus I over h bar, e tau, psi. So now I can just plug that in, and I find psi of t plus tau. Again, I'm neglecting all the other arguments that could go into this for now, but whatever. Dt, psi of e to the minus I e times t plus tau over h bar. Right, because this exponential is just going to give me this exponential times e to the minus I over h bar, e times tau. And so then this just ends up adding tau. Which of course is what we would, it's exactly what we would expect from our original Fourier transform relation, right? I'm just taking psi and psi of t plus tau, and I'm replacing what I had for t before with t plus tau. Sorry, this should be e, not. Okay. So now I want to go ahead and make a point and then wrap things up. It's a bit of a subtlety, but the point is that just like before, since I introduced a Fourier transform pair, I can now, whenever my state is in the time domain, it doesn't really make sense to talk about that state's energy. And so here I want to sort of show an example as to why that is. So say in the energy domain, so in energy space, sounds a little more sci-fi, so we'll call it that. In energy space, say I have some psi 1, which is psi 1 of E1. So that, well, and I'll add another function as well, psi 2 of some different energy, E2. So that when I act with my Hamiltonian operator on psi 1, I get E1 times psi 1. And when I act on psi 2, I get E2 times psi 2. Okay? So, something that we find is that these states, psi1 and psi2, we can sort of think of as initial conditions of the state in the time domain. So for example, I can write psi I, where I is either 1 or 2, at time t equals 0. I'll stop including the dots, just imply that this is 0. This is going to be psi I e sub I. So one way to see this is, this is a solution to the Schrodinger equation. So for example, I can just apply my time evolution operator to find this at time t. So u hat t times psi I e sub I, which is of course e to the minus I over h bar, h hat t, psi I e sub I, which is e to the minus I over h bar, e sub I t, psi I e sub I. And it's pretty straightforward to just sort of plug this in and show that it satisfies the Schrodinger equation. Now keep in mind that e sub I is fixed. That is a fixed number, right? I have fixed e sub I. So big psi, this is sort of an important subtlety. Big psi is not here simultaneously a function of e and t. E sub I is fixed. That is I've chosen the value of e sub I essentially. But anyway, so each of these psi1 and psi2s are solutions to the Schrodinger equation. And since the Schrodinger equation is a linear equation, that means that a sum, or actually, in fact, any linear combination of these two solutions is also a solution. That's actually pretty easy to prove. So I'll write a general psi of t is a1 psi1 of t plus a2 psi2 t. So just a general linear combination, right? Where these a's are each just some number. They can be complex numbers. They can be, I mean, in general, they're complex numbers. But okay, so now I want to look at the Schrodinger equation, which is just psi dt. And I'll write it in kind of a funny way. I'll just bring the h hat side over. I'll bring it to the other side. And this is going to be h hat psi. And of course, I can break this up into two pieces. A1 I h bar d psi 1 t minus h hat psi 1 plus a2 I h bar d psi 2 t minus h hat psi 2. Now I know that each psi 1 and psi 2 are independently solutions to Schrodinger's equation. So this term here goes to 0, and this term here also goes to 0. So the whole thing goes to 0, and I see that psi is a solution to the Schrodinger equation. But now let's sort of go back to looking at this thing's energy, right? So I can, again, just inverse Fourier transform this and look at this general state as a function of energy. And sparing you the sort of more, tedious details, we've done something like this in the past when we first were looking at Fourier transforms. So hopefully it makes sense how we arrived here, but we can just write this in terms of delta functions. Psi1, E1, plus A2 delta E minus E2 psi 2 E2. So you see that now, again, as opposed to what we usually saw in classical mechanics, where our energy was a very well-defined quantity, right? It was, our Hamiltonian gave us the value of the energy at any time. Now we see that our energy isn't a really well-defined quantity, right? We can, in this particular case, this very simple case, the state could be, or the system could be in a state where we find E1. It could also be in a state where we find E2. And so we see that, in general, a solution to the Schrodinger equation is going to live in some superposition state. It's going to live in some superposition of independent, or superposition of states, each of which may have a defined energy, but the total state itself will not, in general. And in fact, this goes for basically any operator we can define. Position, it doesn't necessarily have a well-defined position. It doesn't necessarily have a well-defined momentum, so on and so forth. This is a key thing to keep in mind when we talk about quantum mechanics, known as the superposition principle. And really, again, mathematically, this shouldn't be super mind-blowing at all, right? Because the Schrodinger equation is, it's just a linear equation. So I know that any superposition of any solutions to it has to also be a solution. So a general solution to the Schrodinger equation won't have this very, very special property of having a definite energy, or a definite position, or a definite momentum, any of that. So this idea of the superposition principle is very, very important. And I think this is sort of where I want to leave off this time. I think I gave you guys a lot to chew on with this. But really, the goal of this was to sort of make this step between classical mechanics to quantum mechanics, and see that, quantum mechanics doesn't come from nowhere, right? We see these sort of interesting properties showing up in classical mechanics, and sure, we had to do some logical gymnastics to say, okay, we're going to just say that we're going to replace the Poisson bracket with a Fourier transform. But at the end of the day, the structures were so similar that it was actually a pretty natural thing to suppose. But, there's still quite a lot to discuss here. Like, what does this solution mean? Like, what are these psi's? What does it correspond to? How do I go about solving? Solving the equation is just an exercise in differential equations, so that's more of a math thing. But what are the implications of this superposition principle? Is this even physical, right? Of course, outside of, these live streams, we know that quantum mechanics is a very physical theory, a very viable physical theory. But, as of right now, we haven't made any predictions. What predictions can this make? What do these solutions mean, and how can we extract physics from it? So that's sort of where things are going in the future. Just to sort of give you something to keep in mind for what's coming up. So there's still lots to discuss. Obviously, there's tons to discuss when it comes to quantum mechanics. It's a very rich field, but we are now in the realm of quantum mechanics. I find very exciting. If anyone has any parting questions, I'll hang around for a few more minutes. Just let me know. Anything people want to discuss. Yeah, I think that the main takeaway from this, I think the main thing that I would, if I were to write a single sentence from this, is that quantum mechanics doesn't come from nowhere, right? And only by having a good grasp of classical mechanics and seeing what was happening with the structure of classical mechanics, only through recognizing that were we able to really sort of from quote unquote first principles write down Schrodinger's equation and all of this formalism in terms of operators, etc. But it also doesn't, it's not anything super new. We've done Fourier transforms tons in classical mechanics. Well, okay, tons, meaning we spent an entire stream on it here, but all of the machinery was already in place for quantum mechanics. It was just sort of making this logical step between Poisson brackets to Fourier transform. Yeah, so I think I might call it here. So if you showed up, thank you. Appreciate the support. If you're watching this after the fact, also appreciate the support there, and hope everyone enjoyed. Hopefully I'll see you next time.